This is the first section of chapter 4, kinematics, and this section is all about acceleration varying with time. Now, hopefully you'll remember from the Stats and Mechanics Year 2 book, actually from Year 1, you learned that if you have variable acceleration, where acceleration is a function of time, that we can differentiate and integrate to, integrate the acceleration to get the velocity and the displacement. We can differentiate the displacement, we can differentiate the velocity to get the acceleration. So if we just write down what links all of these, so we know that if I differentiate the displacement with respect to time, that gives you the velocity. The acceleration, that's what you get when you differentiate the velocity with respect to time. Now that's also equal to differentiating the displacement with respect to time twice. And if we move in the other direction, if we integrate the acceleration with respect to t, we get the velocity. If there's no limits, there's going to be a constant of integration. The same with the velocity with respect to time. That gives me the displacement. So with the last two here, don't forget about your constant of integration. So don't forget about C, that constant of integration. And there'll normally be some information in the question that will allow you to substitute some values in to find a constant of integration. So things like initially it's at the origin, or at time equals 2, the velocity is 5. That type of thing that will allow us to work out what the constant of integration is. So let's have a go at some examples. Example 1. A particle P starts from rest at a point O and moves along a straight line. At time t seconds, the acceleration a meters per second squared of P is given by this expression here. The acceleration is equal to 6 over t plus 2 all squared, and in part A we need to find the velocity of P at time t seconds. To find the velocity, we integrate the acceleration with respect to t. The acceleration is a function of t. So we're going to be integrating 6 over t plus 2 all squared with respect to t. Now if I write it as 6 times by t plus 2 to the power minus 2, then I notice that here I can use the reverse chain rule to integrate this because the inside is linear. So let's integrate that and see what we get for v. So what we do is we add 1 to the power, we integrate the outside, so add 1 to the power, it becomes minus 1, divide by the new power, so we're going to be dividing by negative 1, so we get negative 6. Remember the inside of the bracket doesn't change, so it's 2t plus 2, and then we divide by the inside differentiated. That is going to be dividing by 1, so it doesn't change. And then we mustn't forget our constant of integration there, C. We want to find C, so we look back at the question. There's going to be some information that gives a clue. So a particle P starts t equals 0 from rest, v equals 0 at a point O, x equals 0. So these are going to be the values that I use. Well, in fact here just v equals 0 and t equals 0. So t equals 0, v equals 0. We'll substitute those values in and we will get v, which is now 0, is equal to negative 6 times by t plus 2. Actually, let me write it as a fraction. That'll probably be easier to work out with our calculator. So negative 6 over t plus 2 plus c, and now t is 0, so it goes in there, 0. So what have we got? 0 equals, this is going to be negative 3 plus c. That means that c is equal to 3. So now my full expression for the velocity is, and I'll write it like this, minus 6 over t plus 2, or I could write it as t plus 2 to the power negative 1 plus 3. That was the value of the constant of integration. That's the answer for part A. Right, part B says show that the displacement of P from O when t equals 6 is equal to 18 minus 12 log 2 meters. So we need to find what the displacement function is, and we get that by integrating the velocity, which is what we got from part A. So we need to make sure we get part A right. We don't want to be using an incorrect answer in part B. So we'll be integrating -6 over t plus 2 plus 3 dt. Now whenever we get something where the top looks like the bottom differentiated, maybe multiplied by a constant, it's going to be log of the bottom. Now that might be a bit clearer if I actually put the -1 or -6, let's put 1 there, and put the -6 here, then you can see clearly, all right, integrating this part is going to be log t plus 2, and then it's going to be times by -6. So we will now have that x is equal to -6 log, natural log, t plus 2. Now I don't need the modulus because t is going to be greater than 0, plus 2, so this is always going to be positive, so I don't need a modulus symbol, plus 3 differentiated with respect to t, which is just 3t, and then we introduce a constant of integration again. Now strictly speaking, I should use a different letter to the one I used there, so I'm going to use the letter D. Yeah, just go to the next letter in the alphabet. How am I going to find D? Well, I look back at the question. My variables are t and x, and t is 0, x is 0. So we'll use t is 0, x is 0, and we just substitute those values in. So x, which is 0, and then -6, put that in -6, natural log of t plus 2, so it's going to be 0 plus 2, plus 3 times by t, so that's 3 times by 0, plus d. Let's work out the value of d then. So we've basically got 0 equals -6 log 2, so d has to equal +6 log 2. So now my full expression for the displacement is -6 log t plus 2 plus 3t plus 6 log 2. Right, so if we move on to the part where we now substitute in t equals 6, and we want to show that we get this, what might be a good idea is maybe simplify this a bit before we substitute the number in. It doesn't make any odds, we can substitute the number in first, but I'm just going to tidy up a bit because I noticed that I've got 2 logs here which can go together, so we could think of 6 log 2 minus 6 log t plus 2. So 6 log 2, so we've got 6 log 2's and we're subtracting 6 log t plus 2. So we can simplify that to 6 log, almost like the 6 comes out as a factor. And because it's the log 2 minus log t plus 2, this becomes 2 divided by t plus 2. So we're just using the rules for logs there, plus 3t. That's my x. That might be just a little bit easier to substitute in my value of t to find x. Right, so let's do that. So x is equal to 6 natural log 2 plus t plus 2, 6 plus 2, plus 3t, so that's 3 times by t, which is 6. So the last part now is just simplifying this and getting it in the form that they want. Well, obviously that's 18. Let's see what we can do with the log part. Now, the bit in the bracket here is 2 over 8, which is the same as a quarter. So we end up actually with 6 log a quarter. Now, quarter is the same as 2 to the power minus 2. And then I can take the minus 2 and bring it to the front, and then it becomes minus 12. Now I'm just doing the working in red here. If you were doing an exam, you'd probably want to write some of this working out to show that you've done some sort of process to get the value that they want you to get to. But I'm short of space down here, so I'm just showing you that we can get to this, to 6 log 2 to the power minus 2, and from there that will become minus 12 log 2, and you can see that's the other part of what they got here. So I'm just going to basically state what x is. I've done the working at the bottom, and we get 18 minus 12 log 2, so we get the result what they want as required. Example 2. A particle P is moving along the x-axis. At time t equals 0, the particle is at the origin and is moving with speed 2 meters per second in the direction OX. At time t seconds, where t is greater than or equal to 0, the acceleration of P is 4e to the power negative 0.5 t meters per second squared, directed away from O. We'll start with part A, and what we need to do is to find the velocity of P at time t seconds. So velocity, as we know, is what we get when we integrate the acceleration. So the velocity is going to be what we get when we integrate 4e to the minus 0.5 t dt. Right, so when we integrate the e part, we use the reverse chain rule. So integrating the e, it stays as e, and then we need to divide by this power differentiated, so that's negative 0.5. So we're going to do 4 divided by negative 0.5, which becomes negative 8. So negative 8e to the minus 0.5 t plus our constant of integration. Then we scan through the question to find the information. So I've got t equals 0. When t equals 0, it's at the origin, so that means x equals 0. And here it says moving with speed 2 meters per second, so that means that v equals 0. So I will substitute in t equals 0 and v equals to 2. We'll do that and see what we get. So v is 2 is equal to negative 8 e to the 0.5 t, negative 0.5 t, plus c. Now t is 0, isn't it? So let's just correct that and put times by 0, plus c. Now this is the bit where you need to be careful. It is very tempting to write anything to the power 0 as 0, when in fact anything to the power 0 is 1. So the first part here doesn't become 0, it's going to become negative 8. So negative 8 plus c. So that means that our constant of integration is 10. So my full expression for the velocity is negative 8e to the minus 0.5 t plus 10. So that's my result for part A. We'll move on to part B, and it says show that the speed of P cannot exceed 10 meters per second. Now if I were to maybe just flip the two terms around and write it like this, you can see that I'm always subtracting something from 10. So I've put that down in a sentence, and I've also added to that and this part here, this section, thing that we're subtracting from 10 is always greater than 0. This part is always going to be positive. So we're never subtracting a negative number. We're never adding anything to 10, because this part here is always going to be positive. That means that v will not exceed 10. In fact, it's going to be always lower than 10. It's probably going to, I think this part here, as t increases, this value, this part here gets smaller, so this whole expression gets smaller. So you're going to start with like a low value and a number that's getting closer and closer to 10, because what you're going to be subtracting is going to be smaller and smaller. So yeah, the whole thing overall will get closer to 10. And then part C, it says sketch a velocity time graph to illustrate the motion of P. Right, so here's my axis. I need to work out what the value is when t is 0, and in fact it gives us here 2, so it means that our graph starts from 2, and as I've indicated before, it's going to be increasing and getting closer to 10, but it will never reach 10, so we actually need to put a value up here and indicate that this is an asymptote here, that our velocity is tending towards. So let's just draw that. So it's going to be something like this, as I said, getting closer and closer to 10 but never actually reaching 10 as t tends towards infinity. Example 3. A particle p is moving along the x-axis. At time t seconds, the velocity of p is v meters per second, where the velocity is equal to 4 sine 2 pi t. So notice in this question we've been given the velocity. I think in the previous examples it's been the acceleration and we integrate. So here it's going to be differentiate to find acceleration. When t is 0, p is at the origin, find in part A the magnitude of the acceleration. Now it says magnitude, size, so even if our answer is negative we take the positive. So the acceleration is dv dt. That means the acceleration is what we get when we differentiate 4 sine t. So using the chain rule, we'll have 4 cos t times by 2 pi. So that becomes 8 pi cos 2 pi t. And from here we just substitute in t is equal to 2/3 to get our acceleration. So a is equal to 8 pi times by the cosine of 2 pi times by 2/3. Let's see what that gives us. My calculator gives me negative 4 pi meters per second squared. Now it says the magnitude, so I ignore the negative, and the size of the acceleration is 4 pi meters per second squared. Let's have a look at part B. The greatest distance from O attained by P during the motion. Now, sometimes when we're asked to find the greatest distance, we can look to see when the velocity is 0. But when we have these types of questions where the velocity is sine or cos, then because we know the maximum and minimum of the sine and the cos graph, we can use that to work out the greatest distance. So what we need to do to find the greatest distance, we need to integrate the velocity. To find the displacement, so it's going to be like cos or something like that. So we're going to be integrating 4 sine 2 pi t with respect to t. That will give us, let's see, so we integrate the outside, that's going to become negative cos. The inside of the bracket doesn't change, but then we divide by this differentiator, so we need to divide 4 by 2 pi. So 4 over 2 pi, let's write it down here, 4 over 2 pi is going to be the same as 2 over pi, and we've got that negative there, so let's put negative 2 over pi, let's get it right. And then we plus our constant of integration. Here, I think on a previous example I used C for part A and B when it was integrating. We should really use different letters to indicate that it's a different constant of integration. How am I going to find that? Well, we look back at the question. When t is 0, p is at the origin. So there's our values. T is 0, x is 0. We plug those in. So x is 0 is equal to negative 2 over pi cos 2 pi times by t, which is 0, plus c. So we can work out what c is. So here we've got the cosine of 0. Remember, the cosine of 0 is 1. So this whole part here is 1. So we basically have 0 equals negative 2 over pi plus c, which means that c must equal 2 over pi. So my full expression for the displacement is negative 2 over pi cos 2 pi t plus 2 over pi. And we want to use this here to find the greatest distance. Now the distance is really sort of, it's this part that's going to make the difference to displacement. So let's just annotate over it. This part here is going to be the part that changes. That will be going from +1 to -1. Okay, it's going to be between those values, and we want to work out, is it the +1 or the -1 that's going to give us the greatest distance? Well, we've got this 2 over pi here. We're going to get the greatest distance when we can add another 2 over pi. That's going to happen when the cos 2 pi t bit is equal to -1. So I'll just put greatest distance is when cos 2 pi t is equal to -1. We actually just want to know what the greatest distance is. That's basically going to be the -2 over pi times by -1 plus 2 over pi, which is 4 over pi. So that's the greatest distance. I'm sort of doing a little bit extra really. I'm finding, or I could find, the time at which that greatest distance occurred, and then I would go on and solve this equation here. So I don't need to solve this to find the value of t. I just need to figure out what's going on here. How am I going to get this to be its maximum? And that's going to be when this part is -1. So you get plus 2 over pi plus another 2 over pi. Greatest distance is going to be 4 over pi meters, my greatest distance. Example 4. A particle P is moving along the x-axis. Initially P is at the origin O. At time t seconds, where t is greater than or equal to 0, is positive, the velocity v meters per second of P is given by v is equal to t times by e to the power -t over 4. Now I might write that a bit bigger because you might not be able to see that. So we've got v is equal to t e, and the power is -t over 4. Find the distance of P from O when the acceleration of P is 0. So there's a few things that I need to do. I actually need to find the acceleration. So I need to differentiate the velocity, find the acceleration, and then I'm going to set that acceleration equal to 0. Okay, when I've set that equal to 0, I'm going to use that and find the time at which the acceleration is 0. Then I'm going to integrate my velocity. So I will integrate my velocity to find my displacement. I will then substitute that value of t after I found a constant of integration into this to work out what that distance is. So there's some differentiation and integration. So first of all, let's work out what the acceleration is. So that's going to be dv dt. So a is equal to, now we'll use the product rule to differentiate this. I'll do some working over here. So let's make u equal to t, v equal to e to the minus t over 4. So u dash is 1, v dash is going to be at -1/4 e to the minus t over 4. So my acceleration is going to be u v dash, so -1/4 t times by e to the minus t over 4 plus v u dash, so that's just going to be e to the minus t over 4. We want to find the time at which the acceleration is 0, so we just set our expression -1/4 t e to the minus t over 4 plus e to the minus t over 4 equal to 0. This will be easier to solve once we factorise it. So we'll take out the e to the minus t over 4 out, and then in brackets I will have, and let's write it this way round, 1 minus a quarter t, or t over 4, equal to 0. Now e to the minus t over 4 can never be equal to 0, so that doesn't give us a solution. So we look at the 1 minus a quarter t equal to 0. So that means that a quarter t is going to be equal to 1, which means that t is equal to 4. So this t equal to 4 represents the time when the acceleration is 0. Now we'll set this aside for the second bit, so I'll just highlight this in yellow because we'll need this for the next part. So we'll work out now the displacement, and the displacement is what we get when we integrate the velocity. So that's going to be integrating t times by e to the minus t over 4 dt. And this one, where we've got a product like this, and one part is a polynomial, normally like x or t or x squared, t squared, we're going to use integration by parts. So integration by parts, I'll do my working over the side. So we know that when we do integration by parts, we set either the log part or the polynomial part equal to u, so u is going to equal to t, and we set the dv dt part equal to the e to the minus t over 4. So we differentiate the u part, so du dt, and that will give us 1, and then we integrate the dv dt part, so that's going to be the reverse chain rule. So I'm still going to have e to the minus t over 4. I divide by that power differentiated, which is going to be a quarter, divide by a quarter, which is the same, or divide by negative a quarter, which is the same as multiplying by negative 4. So now we'll do our integration by parts, and that will give us x is equal to, now it's uv, so it's minus 4t e to the minus t over 4, that's our uv part, minus, and it's going to be integral of v du dx, so it's basically just going to be this here, because it's just going to get times by 1. And I've got minus 4 constant, so let's take the minus 4 over to the other side. So we're going to write a plus 4 over here. There's no point writing minus 4, so we'll just put plus 4, stick any constants on the other side. It looks easier, or if it looks easier, it's going to be easier, like that. So we're just left integrating this, and we've done that already, so we can just copy this down here. We've already integrated it. So x is equal to minus 4t e to the minus t over 4, and then we've got 4 lots of this, because this integrated, which is this integrated, is this. So we've got plus 4 lots of this, so minus 4 e to the minus t over 4. And we mustn't forget with our integration that we have a constant of integration, we haven't got any limits. We now want to find our constant of integration before we substitute in the t equals 4 to find what this distance is, what this displacement is here. And we can use this bit of information here. Initially t is at the origin, initially t equals 0, at the origin x equals 0. So we will substitute those values in, t equals 0, x equals 0. So we will have 0 is equal to, now we won't write all the zeros in here, we'll see if we can work it out. So this is just going to be 1, this part here, then it's going to get times by 0, so all of this part here is gone, there's no point writing it down. Then this part here, this part, the e to the power part, is going to be e to the 0, which is 1, so we're going to have negative 4 times by plus 4, so we've got negative 16. So all that's left is negative 16 plus c, which means that c is equal to 16. So my final expression for x, before I factorise it, actually shall I factor it? Yeah, let's factorise it. So e to the minus t over 4. Now this term here has minus 4t, so I'll put minus 4t. And then this term here is going to have minus 16. So we'll put in minus 16. And then plus 16 for our constant of integration. Now thinking about it, I could have actually taken a minus out as well, it doesn't matter. So the last thing now is to substitute in that t equals 4. So we take this answer and plug it in here and see what we get. Hopefully got enough space just to work it out. Right, so here when t is 4, we'll have e to the power minus 1. So write that down. E to the power minus 1, negative 1. Then in the brackets here, we'll have negative 4 times by 4. So we'll have negative 16 times that by another, or take away another 16. So this bit in the bracket ends up being minus 32. So let me just check that. Negative 4 times by 4, negative 16. Minus another 16, yeah. So that's going to get times by negative 32. And then we're going to add 16. I suppose I could tidy that up a bit, but that will do. That is going to be what the displacement is, what the distance is when the acceleration is 0. Example 5. A particle p is moving along the x-axis. At time t seconds, the velocity of p is v meters per second in the direction of increasing x, where v is given by this piecewise function. When the time is between 0 and 2 seconds, its velocity is given by 2t. When time is greater than 2 seconds, its velocity is 2 plus 4 over t. And it says when t is 0, p is at the origin. And what we need to do in part A is to sketch a velocity time graph. So let's just draw our axis, velocity and time, and let's sketch each part separately. So we start with the first one, which is just between 0 and 2 seconds. Now this may not be to scale, it's just a sketch. And it's linear. First part there is linear. It's going to be a straight line. And where does that straight line go from? Well, it goes from 0, 0, because when t is 0, v is going to be 0, 2 times 0, so it starts down here, up to 4. So it's actually going to be a straight line from 0, 0 to 2, 4. So let's mark 4 on the axis here, and let's draw that line in. I may need to move that 4 up or down depending on what the second part of the graph looks like. So the second part here, I've got 2 plus a reciprocal. Now, what do reciprocal graphs look like? Well, for positive values of x, in this case positive values of t, reciprocals look like this, don't they? They go down. So this part, let's just like that, is going to look something like this. But the 2 means that this reciprocal graph gets shifted up by 2. And what will happen is that this reciprocal shape is going to be over here, and it's going to continue where the last graph finished, because I know this is greater than 2, but if you put 2 into this to see what happens as t approaches 2, you'll get 2 plus 4 over 2, 2 plus 2 is 4. So it starts just after 2, and it's going to be this reciprocal graph that goes down. Now we don't need to draw this forever, because we only need to draw a sketch between 0 and 5 here. So it's going to stop at 5. And what we want to work out is how far down it's gone here. So what we do, we're going to put 5 into this function. So we can work out what v is going to be when t is equal to 5. So that'll be 2 plus 4/5, or 2 and 4/5, or 2.8. So we'll mark that in on the axis here. So it's actually just reached down to 2.8. So on my graph, it should actually be touching 2.8 by the time it gets to 5. So something like that. Right, so we'll move on to part B. Part B, find the distance of P from O when T is 5. Right, because we've got this sketch of the velocity time graph, the distance is going to be given by this area here plus this area. So what we're going to do, we're going to find both areas. Now the first one is straightforward because the area of that, it's just a triangle. So it's just going to be half base times height. So half base 2 times by height 4. So that gives us 4 meters. So this displacement here is 4 meters. And then the displacement for this part, we need to use integration. So we'll integrate the second part of the piecewise function, 2 plus 4 over t, and integrate that with respect to t between the limits of 2 and 5. So the 2 will become 2t, the 4 over t will become 4 log t, and we will substitute in our limits of 2 and 5. So we put the 5 in, that will give us 2 times 5, 10, plus 4 log 5, and then minus 2 times 2, 4, plus 4 log 2. We can simplify that, so the 10 minus 4 is going to be 6, and then 4 log 5 minus 4 log 2 is like having plus 4 lots of log 5 divided by 2, log 5 over 2, so log 5 over 2. Then the complete displacement, so total is going to be my 4 plus the 6 plus 4 log 5 over 2. So that gives me 10 plus 4 natural log 5 over 2. And that will be in meters. So remember the area under velocity time graph is the distance. Example 6. A particle P moves along the positive x-axis. The velocity of P at time t seconds is 2t squared minus 7t plus 3 meters per second, where t is greater than or equal to 0. When t equals 0, P is 10 meters from the origin, and in part A, what we need to find is the value of t when P is instantaneously at rest. So something's going to be at rest or instantaneously at rest when V is equal to 0. V is 2t squared minus 7t plus 3. We set that equal to 0. We could use our calculators, but I think this is going to be easy enough to factorize because it's got to be 2t and t. I want 3, so I need a 3 and a 1. I want 7, so the 3's got to go in the second bracket. That'll give me 6 and 1. And I want minus 7, so they've got to be 2 minuses. So that means that either 2t minus 1 is equal to 0, and that will give me 2t equals 1, or t is equal to a half, and then it's t minus 3 is equal to 0. So my other value is going to be that t is equal to 3. So t equals 3. So these are the two times t is a half and t is 3 seconds when it's at rest instantaneously. Part B says the displacement of P when t is 5. So we want to find the displacement. And that's really, when we're doing displacement, we should use s instead of x. X is going to be distance, so we'll use s here. But you know, I'm sure you won't lose marks if you use x, but really displacement should be s rather than x. So s is going to be what we get when we integrate v with respect to t. So s will be equal to 2t squared becomes t cubed. Let me divide it by 3, so it'll be 2/3 t cubed. Then the minus 7t will become minus 7 over 2t squared plus 3t. We will have a constant of integration. We want to calculate that constant of integration, and it says when t is 0, the displacement is 10. So when t is 0, we have x equals 10. We'll substitute that in, so we'll have 10 is equal to 2/3 times by t cubed, 0 cubed, minus 7 over 2 times by 0 squared, plus 3 times by 0, that's all handy, plus c, so that should be nice and easy. That gives us that c is 10. So my full expression for the displacement is s is equal to 2/3 t cubed minus 7 over 2 t squared plus 3t plus 10. And we want to find the displacement when t is 5. So all we need to do now is to substitute in t is equal to 5. So s will equal 2/3 times by 5 cubed minus 7 over 2 times by 5 squared plus 3 times 5 plus 10. I'm going to do this all on my calculator to get s. And I get 125 over 6 meters. I can leave it like that or give an answer to 3 significant figures or some sort of decimal. So that will be my displacement. Okay, part C, it says, can we work out the total distance travelled by p in the interval 0 to 5? Now we need to be careful because there are times when the velocity is 0, and normally what happens when the velocity is 0 is because something has changed direction. So it's probably that the path of this is that it goes forward, then the velocity 0 changes direction, then the velocity 0 again, and it changes direction. Yep. So that means here we've got t is equal to 0, that's the start. Here is t is equal to 5. And these points here, when it was at rest, we're assuming it's changing direction. T equals half a second, and t is equal to 3 seconds. We can't just integrate from 0 to 5, because all we'll get is this displacement distance, which is incorrect. We want the distance. So actually, we're going to have 3 separate bits of working. One that gives us this, we integrate between 0 and a half. Then we're going to integrate between half and 3. And then finally we'll integrate between 3 and 5. We have to do that because we know it's changed direction. Or we assume it's changed direction. We don't know or not. But we must separate out each one of those integrations. So we'll start by integrating between 0 and a half. Now we've already integrated the velocity, so we know what its expression is, okay? Now we've got limits, so there's going to be no plus c. So it's just going to be this part here that we have, and we substitute in our limits. So let me see if I can write this all out. So our distance is going to be given by substituting in 2/3 t cubed minus 7 over 2 t squared plus 3t between limits of 0 and a half. Okay, now just to be safe, I'm going to put modular signs around these because I only want positives, because I want to add the positives, because I'm guessing that when I work out this part here, I'm going to get a negative displacement, but I want to make sure that I add it on. I want a distance, so this plus this plus this. So just to make sure, around each part I'm going to put a modulus. Plus, just trying to grab whatever space I can, the modulus of, making sure I get a positive, 2/3 t cubed minus 7 over 2 t squared plus 3t. But this time the limits are between 3.5, half and 3. So again, modulus sign. Then the last one plus, last modulus. This is where we integrate between 3 and 5. Same expression again. So 2/3 t cubed minus 7 over 2 t squared plus 3t. And our limits are 3 and 5. Again, the modulus. Let's work out each one of those parts and see what we get for our final answer. Right, so for the first one, between 0.5, doing it on a calculator, we're going to get 17 over 24. And that gives us a positive anyway. For the second one, between 3.5, we actually get negative 125 over 24. So we're going to put the plus, and then it's the modulus, the positive of 125 over 24. And then we add what we get when we work out this one here, the limits between 5 and 3, and that will give us 46 over 3. Now if we add all three of those together, 85 over 4 meters. I suppose I could do that as 21.25 meters. So some questions, they don't tell you that the velocity is 0. Sometimes you need to check and do that, but the clues in the first part, instantaneously at rest, is a clue. When I work out the distance, I'm going to have to add together all of the displacements, making sure that I take the positive value for the displacement. So don't let things like this catch you out. Often the clue is when the velocity is like a quadratic or a cubic or a quartic, something like that, something where we're going to have roots to it, and those roots are going to be the points at which it's possibly changing direction. In this case, yes, it is changing direction. We could probably sketch that velocity graph out, and that would tell us that. So you should now be able to work out exercise 4A on pages 153 to 155 of the textbook.